And first of all, I would like to thank the organizers to invite me here and to provide this wonderful space here and welcoming me. Yes, I will talk about ocean observing design, and you heard last week already at least 2 or 3 lectures on ocean observing design on general aspects related to the global ocean observing system, and also on particularities on observing design for specific small-scale features, like the Borean front here south. Simon Ruiz presented that. And also on biogeochemistry and ocean observing design. It's very, let's see, well, yeah, it's okay. Okay. First of all, I would like to introduce briefly myself. So, Johannes Karstensen was already said. And actually, I studied physical oceanography in Hamburg at the University of Hamburg. And from there, I moved, or during my PhD, actually, I moved to Australia and worked for a while in Australia on Indian Ocean topics. Then I returned back to Hamburg, finished my PhD, and I moved actually to the US, to Lamont, where I worked I worked on observational data, but that was observational data from the Greenland Sea, from the very high north. Returning back to Germany, I started a position in Kiel, but only very briefly, and then I turned to the southern hemisphere, working in Concepcion in Chile, on issues related to water mass transformation observational data in the Southeast Pacific and Southern Pacific. And after Chile, I then moved back to Kiel, where I am since then. Time to move, I think. So what you can see on the right is, that doesn't work, the last 8-9 years of cruises I've been doing. These are the cruise tracks. I'm primarily looking into physical oceanography and also biogeochemistry associated with physical oceanography processes in the subpolar North Atlantic, but I'm also looking into things in the South Atlantic very recently, tropical Atlantic, and also still in the Southeast Pacific, using ships and other observing techniques. This is actually where then I, of course, try to optimize the way observations I perform should be done in order to save money, save time, and get the best out of it. So my talk outline is that I will present some basic principles about observing design, very, very basic, but I think it's good to reconsider that. Then I will present some really specific strategies on ocean observing design in the framework for ocean observing context. The framework for ocean observing, I will not really go into that because it has been presented already. And in particular here, I will say how mapping of the ocean is being used to design observing. And this will be done through the Argo example. Argo you've heard a lot of times already. Very popular in assimilation models and in operational oceanography. Then I come to another kind of example, which is observations from, I would call them, opportunistic networks, not designed, but composed. And then I will briefly say something about ocean simulation, observing simulation experiments for the assessment of observing design. From there, I come to more problems rather than solutions about multidisciplinary and multi-platform observing, and then I end up with some conclusions. So really going very, very back, what you see here is an ocean color satellite retrieval picture from the Southwest Pacific on the 30th of March 2016. And of course, you have seen all these pictures a lot of times. What is interesting is that you see these very, very, scales, these very different scales, and you can identify immediately that there are features like these, which are on the scale of 300, 200 kilometers, which is the so-called mesoscale. I would like to emphasize here, this is ocean color. So this is, first of all, nothing really physical, but biogeochemical. It could be, for example, the imprint of some chlorophyll or coccolithophora or whatever organisms in the water. If we zoom into a region like that, we can see that it's filled up with other features, like, for example, these more or less 20-kilometer scales. And if we further zoom into that, we can see that filaments like that are also surrounded by other filaments which have even smaller scales. Again, this is biology in certain ways, what we see here. And this already tells us that if we would like to do something, if we would simulate or assimilate biology, physics is the primary objective, and then biology is added on. So in other words, if you do not do the physics right, then you will end up not in the right picture here. But there are myriads of scales included, we all know that, and they are all interacting. They are interacting with each other in, for example, physics, but they also interact across disciplines, so physics, biology, chemistry, geophysics, they are all interacting. So that is quite a task to design now observing strategies in order to capture these processes. So that's really very basic, but I think still, as I said, it's very worth to remembering it. So what we do in ocean observing, or in general in quantitative science, is that we, first of all, we collect some information, like the satellite retrieval I just showed. Then we look at it, and then we start to formulate and ask questions about it. Based on these questions, we start to formulate a hypothesis. The hypothesis then ends up, this is a very important step, in a certain design experiment, or design of an experiment, in order to somehow prove or not, depending, the hypothesis. So we design the experiment, we conduct the experiment, then we will see if that experiment actually looks like we expect it to happen, or if it doesn't look like that, right? So if you look very closely, you can see that at least the expectation of having this kind of level here is also shown here, but there's a lot of noise on it. So you have to decide whether you compare your expectation to your observation, and then you have to compare, you have to decide whether, well, that was okay, the experiment, so I can think that these hypotheses are actually correct. So I report that finding, another important step. I reflect with the community, I will publish that, and others may do similar experiments, and the hypothesis is getting better and better, or it's getting at least more solid. Or I think, no, that wasn't right. And then I need to either change my experiment or also refine my hypothesis. And then go through the same thing again. So at the end, what comes out here is that we have a certain hypothesis about the functioning of the world, more or less. This is for qualitative or quantitative science, right? So we try to structure our physical world into pieces of hypothetical functioning in order to allow to predict the functioning of a certain piece according to the hypothesis that has been posed. This is, of course, super general, but that's how scientific knowledge is being created. And we always have to rethink about it, right? That we are really starting with certain hypotheses, and we shouldn't overstress them, because that will end up in drawing conclusions based on the wrong hypothesis. So why do we observe that? Why do we need these hypotheses? There's, of course, scientific interest in it, just intellectual interest. We want to understand, in particular for the ocean, how can we explain the present state of the ocean, the past state of the ocean? How can we, for example, differentiate between natural versus anthropogenic changes or states in the ocean. We would like, as a research driver, to understand interactions between different disciplines. There are, of course, natural sciences like biology, chemistry, physics, but we also want to understand the interaction of these sciences, for example, with economy. Economy has also models, and we can interact with them. The same is true for social sciences. And finally, of course, we would like to predict and forecast future state, which is a big, big thing in operational oceanography. Well, then there is another driver, which is more like a technological driver. That is also important for society, I think. It also is somehow a little linked with the research. There are drivers like big data, so we want to collect a lot of data in order to test or with a hypothesis, but maybe also to detect certain connectivities between hypotheses we haven't seen before. Technology also includes development of sensors and improvement of sensors and platforms to observe the ocean. It includes cost efficiency, and so we would like to make sensors miniaturized. It also includes education and training. You could put it here, maybe also in the other disciplines. So these are elements why we observe that from, let's say, the research perspective, technology perspective, but somebody has to finance it, right? And so we always have to consider the societal drivers that help us to perform these two things. Societal drivers are listed here. There are many, many more. Food security, population growth, energy and transport, human health, maritime economy, ecosystem services. I mean, we heard about all that also in the past days. So this is our, say, gross intention why we observe. But the question is now how to structure that. We have certain hypotheses, we have scientific knowledge, we have the society that wants questions, that wants answers or information about certain issues. And now we need to do our experiment. This you have seen already. So this is the very, very basic graph from the so-called framework for ocean observing. So this is more or less a society here. That's what they want. And then we have our knowledge, actually partly the scientific hypothesis is partly in here, defining these requirements and defining the input. Then we have all the observations and technology development in this block. And out of here, the data is being used, for example, in assimilation models to predict, to create output product. And that, of course, is then being reflected back into what the society wants. So if you look into this framework of ocean observing, you will see something like the framework guides the path from the science-driven requirements resulting from societal issues, so this is not really the sequence, identifying the observation, deployment, and maintenance needed for the production of impactful and relevant tools to address the societal issues. So the sequence is, first you have to identify what is society being interested in, financing. Then you evaluate your scientific knowledge, your hypothesis, that are linked actually to the certain questions that has been asked here. It is only probably one question, fishery success. And then you come up with an estimate of an observing solution for the scientific hypothesis. You execute the observing, you perform then product generation and validate the whole thing. So I would mainly talk about these evaluation scientific knowledge and estimating observing solutions. So for general, there's a general sequence now also for designing observing in a global ocean observing, so in a sustained observing context. First, one needs to develop a certain observational analysis, a technique, an approach, a hypothesis. Of course, that comes out just from curiosity, from really science. that is done actually within the ocean science community. But it needs to have, of course, acceptance within the community about the methodology you're using, and that actually has to come from experience within pilot projects. Only through that you can demonstrate the utility of methods and data. Followed by that, if you have the acceptance, then you can enter with your observational approach into a kind of pre-operational use of this method and create first products to end users, researchers, application groups, could be whatever the society wants. And that, of course, in this context here, and this is where most or many of the operational oceanography depends on. So in the GOOS context, you need to have the proper integration of your system and the pre-operational use into the global system. Of course, what also needs to be considered if you come up with a new method, that there will be no negative impact on, say, integrity, on what is already out there. And finally, you incorporate that into an operational framework, your pre-operational strategy, and that hopefully will get sustained support because it should meet in a sustained way societal objectives, fishery maps, something. So what is often being done in the sequence in coming up with an observing design is something which could be called the mapping approach. It's probably wrongly written. Okay. So this is now the approach that is also being used, for example, for Argo design. I will come to that later, but also for other design. So what this mapping approach does is that it tries to estimate a true value, for example, temperature or temperature anomaly, whatever, at a certain grid point. For example, 2 degrees lat long. And that true value, where to get it, you can, for all pieces of the ocean, you maybe can create a true value, if you increase that, for example, here, by interpolating all hopefully randomly distributed values around in that area. So you will get a mean value, and you will also get noisy observations about that true value in that grid node. So if you now minimize mean squares of this interpolation error at that grid node, what you will get is interpolation weights to that value. For example, if there are many, many points very close to each other, and then 2 rather far, you need to weight the importance of these points relative to representing the whole 2 by 2 degree square. If the weights have been determined, which depend on the covariance of the values, time and space, in this little square, and you also consider, as I just said, the density of the observations, then, voila, you will get a covariance that is, say, the least sampling rate that yield any desired interpolation error that can be estimated from it. Because you can just say, okay, if I want on a daily basis temperatures within 0.1 degrees being determined, then I need to have a certain least sampling in order to come up with that result. So that actually then leads into objective, based on the underlying data, recommendations for a minimal sampling requirement that answers desired acceptable interpolation errors. So one example here is Argo. For the Argo design, actually, what has been done was to analyze temperature data from XBT, CTT, MBTs, so different types of observations of temperature sondes. This is an XBT sonde for those which haven't seen that. that's launched from a ship, and it measures 400, 500 meter temperature distribution or profile. And what was done actually for the Argo science plan was to analyze about 30 years of these temperature data. And what was found that zonal decorrelation of the temperature data indicated that about 12 degrees of zonal decorrelation were found, which is primarily because zonal currents are very dominating currents. Meridional decorrelation was much smaller, 4 degrees. There was a noise variance of 0.1, 0.8, and a signal variance of 0.2 degrees. So how does that look? So this actually is the XBT data for the Pacific, for example, based on creating an error map based on these scales here for the Pacific. And the numbers you see here is now the error in temperature that is found if these scales are applied. Right? So the error along the lines here where you see the dots are all the observational data, the error is here less than 0.5 degrees. So this is the gridding that has been done for a 2-month period, a typical error map. Okay, is 0.5 degrees good or not good? I will come to that. This now is a hypothetical error map from a distribution, randomly distributed array of profilers with the same decorrelation scales and noise variances. And what you can see is, of course, if you put a lot of these profilers in here, the error is always more or less than 0.5 degrees. That's good. So the conclusion then is, okay, 0.5 degrees, if I integrate 0.5 degrees error over a 50-meter thick layer, I end up in having an equivalent heat flux, of 15 watts per square meter. 15 watts per square meter was, at least at that time when the science plan was written, kind of the typical net heat flux error. So in other words, that system here with such floats would provide you with an estimate that is probably even better than what you get anyway as an error from net heat flux estimates. Okay, the consequence out of that was to ask for a system that profiles between 30 north, 30 south, upper 2,000 meters actually, to capture all the warm water sphere with a 10 days profiling sequence in order to satisfy this idealized map you can see in the background. This design is really being done by having only one platform, which is Argo, and that platform is responsible now for the information that brings out the changes in heat content on seasonal timescales. So I go again through that. So the high-level objective, because I think it's very important to really remember that, the high-level objective of this Argo, I call it here Argo Climate, because that was the original intention, was really to understand ocean warming on multi-annual timescales, because that was asked actually from science, but also from the society to know. Climate. Then what has been done and been outlined in the science plan in collaboration with the community was to estimate these upper ocean heat content changes on seasonal and longer timescales as an indicator for ocean warming. Warming is, of course, not the same than heat content. Heat content is already a concept, while warming is just, put in the thermometer. And, of course, the sampling also needed to consider that there is a mesoscale field on top of it, and you would also want to know how deep temperature and heat content variability reaches. So you need a vertical profiling. Then the scientific knowledge, the hypothesis was being kind of revisited, and a certain approach was being selected. I just outlined that with the temperature anomalies about the annual mean cycle and so forth. And then the recommendation came out. But it's very important to really remember that this recommendation is 3,000 floats, profiling 10 days, is something that is really based on climate only, right? I fully respect and understand that, for example, assimilation models like Argo, because it's data that comes in more or less regularly spaced and regular also in time, and that it's sort of more easy to integrate that into an assimilation procedure. But it doesn't mean that we can, for example, use these numbers for all different problems being posed here. For example, oxygen variability in the ocean by equipment of Argo profilers with oxygen. I think it's super positive to do that, but remember that this gridding here has nothing to do with the oxygen objective. And first of all, I would like to see if oxygen would behave like temperature anomalies, which I haven't seen so far. But that was actually already recognized in the science platform Argo. It's a global, broad-scale network measuring physical state variables of the upper ocean for climate. So it's only for climate. And it was also recognized there that you need, of course, other sampling methods for the upper ocean, satellite observations, moorings, whatever other important elements, for example, to measure air-sea fluxes of momentum, heat, water, all that. You need to measure western boundary currents, which are probably not being very well measured, depending on your scientific objective, with Argo floats, or equatorial waveguide likewise, and in particular also small-scale features. Abyssal ocean is also a question if Argo is really the solution for that, and the same is, as I just mentioned, biology and biogeochemistry. Local or regional process studies, of course, that also need different approaches, but it's probably more accepted for regional node, as, for example, you've seen that by the presentation from Simon Ruiz. There are many more not listed here. So other networks, this is a network which I call, it's not a designed network, so there isn't any specific objective for the whole network. But this is a network of open ocean moorings. So you all have seen a mooring, a line where you add different sensors to. Eventually you have real-time access to the data of that line. And this is a global map of moorings within the so-called ocean sites context. So as I said, it's not based on a single design like the Argo example I just showed you, but there are about 300 sites and maybe 80 different objectives, maybe 200 different objectives locally. But, of course, you can kind of identify certain similarities between what all these different platforms trying to do. And one could group that into boundary current or transport mood arrays that measure the flow and the properties in a certain choke area, outflow from the Red Sea, for example. That might be a good place where you could add a transport mood array in order to monitor that outflow. There are air-sea flux reference sites, which are very complex sites with very highly sophisticated surface meteorological sensors that measure different meteorological variables. And then there are long time series, Global Ocean Watch, which provide you with 10, 20, 30, 40 years of physical, biogeochemical, and biological data. What makes it really a network then is that these networks try to implement data and platform interoperability. So that is closely linked to exchange of knowledge, to follow certain standards for how the instruments are being deployed and so forth. And of course, the availability of data the format the data is being made available is a big, big part of the network. And in addition, this network needs also to communicate, for example, with Argo and other networks, and that's also being done through this network approach in the context of the so-called GEOMAR, which is the organizational part from the GOOS observing platforms. And then a last point, which is also very important for a network, is that you do capacity building, and as said already, knowledge transfer related to the platform, the deployment, the maintenance, setting up new sites, and so forth. Okay, so these were examples of two different types of observing platforms, and then I give you with a mapping a kind of approach how to design a network like Argo. There are other approaches, observing system experiments. Yesterday there was already being touched on that in the Jacob's talk yesterday, and I think today as well, yeah. There are, of course, limitations in mapping decorrelation approach. If there's, for example, no data, how would you do mapping of decorrelation skills? That doesn't work, right? So another approach is to assess and compare operation observing system in a control software environment. That means that what you do in these observing system simulation experiments, as they are called, you've seen that already. On some base, often this is a numerical super high resolution model simulation, you create something which is called a nature run. This nature run is being thought it's a truth, it's a nature. And then you sample that nature according to an envisioned, somehow observing design. And so what you create out of that is artificial observational data. These artificial observational data is then used in your product generation scheme to create, for example, a map or to create whatever product. But the advantage now is that you can create that product, and you can compare it with the real, you can compare the real nature run with the artificial outcome and quantify the error of the, in this case, subsampled nature run. And that gives you really a quantification of the error. But of course, it needs to be considered that this is just a nature run that probably has not the whole complexity of the ocean in it. I found that to be a very interesting other approach, which doesn't rely on actually real modeling data. What they did here was to use daily sea level anomaly maps measured with a satellite, and then subsampled the maps and looked into the subsampled the maps and made a mapping of the subsampled maps in order to reconstruct on a different scale the sea level anomaly. So then they compared here this reconstructed sea level anomaly with the nature run, the observed sea level anomaly, in order to see how to improve actually the sampling of sea level anomaly in the Mediterranean. This sea level anomaly in this case was used as a metric for mesoscale eddies. So the question was, how good is that sea level anomaly really being resolved by individual profiles? It was again addressing the Argo density. So what you can see here, this is the original sea level anomaly, and these are different realizations of the gridded field based on randomly distributed observations of that map. And it can be found, which I think is interesting, that if you have 450 of these floats, that produces you equivalent of sea level anomaly in the ocean. then you will get these characteristics: an RMS error of 3 centimeters of the sea level anomaly with considering 150 kilometer resolution. And that actually would reduce the RMS error by about 40% if you compare it to the current coverage of Argo in the Mediterranean. The very interesting conclusion also was that they estimated, of course, because of the increase in the floats, you will need about a factor of 6 more investment into floats. But actually, these numbers really matter to the society, right? Okay, so I introduce now also the OSSE as a kind of verification approach, I would say. And now I come to multi-network interdisciplinary observing. This you also have for sure seen. I haven't seen that here, but this is for physics a so-called Stommel diagram. What you can see, different processes, capillary waves. Yesterday we had the internal tides, surface tides. So they are operating on time scales of about half a day, as we heard, to about a day or 2 weeks. No, about a day, and on scales from about 1 kilometer or less to about 1,000 kilometers, the whole basin scales. And then you can orient everything: internal gravity waves, shorter mesoscale and eddies, and so forth. Global warming is long time scales and large horizontal scales. Okay, so I just briefly introduced you to this sampling, and I outlined an opportunistic network like that, but we have, of course, a lot more of these networks, and we have satellites, and we have this sampling problem here. So we put all these different capabilities of sampling, time and space, then you can see that combining all different observing platforms on the left pretty much matches our scales we need to observe, right? So it's a mixed system, actually, that is where the secret is. So comprehensive observing design requires a combination of all these platforms. There are, of course, other problems than just combining scales. There is, for example, a limited commonality, I would call it, in the quantification, in the way we quantified certain processes in physics, biology, and chemistry. We have Navier-Stokes equations that helps us at least to have a framework for all motion in the ocean. I mean, they are super complex and they are not really solvable, but at least we know how this framework should look. This is a little different for biogeochemistry, for example, and even less clear for biology, because there is no quantitative closed system available. Of course, as we heard it this morning, you can use like an NPZD model to somehow model energy transfer. But it was also outlined this morning that this is not really a chemistry model. It also includes, for example, zooplankton, which is already biology, right? It's not chemistry. So, and if you have biology, then it gets very much in stochastics and all that stuff. So it's really, kind of difficult to bring these things together just because there's not one single system of equations. So in order to approach that problem, what has been done actually recently was to organize a workshop and bring people together to think about some focus themes. And some in the room were on this workshop, and we had 3 themes actually. It was plankton community changes. It's a highly multidisciplinary problem. Oxygen minimum zones. I will go into details about that in a second. And also open ocean shelf and coastal ocean interaction. Again, super multidisciplinary in scales and also in the processes. So these experts of multiple of these disciplines were put together and start thinking about how to develop observing techniques for a multi-platform, most likely, and also multidisciplinary problem. And I will just briefly introduce you into that oxygen minimum zone problem, because I was involved in it. So first, as I said, first we identified what is the kind of overarching high-level objective. That you need to define that first, before you start thinking about how to tackle that in terms of observations. So that was our objective. How do changing oxygen minimum zones already affect the spatial temporal distribution, productivity, and trophic structure of benthic and pelagic communities? So water column, and also benthos, also the seafloor communities, and how do they interact with oxygen and variability and so forth. So you can see already this is quite complex. I will show you a few examples of the complexity. This is the view nitrogen cycling, for example, occurs in oxygen minimum zones. The specific thing here is that because it's oxygen deficient, nitrogen cannot be really normally remineralized, and oxygen cannot be used for respiration, and therefore other processes like so-called denitrification, anamox take place, right? In unknown rates, in unknown exchanges. This is now the point of view conceptually from a biogeochemist. If you ask somebody who's in genomics, he will tell you this works like that. So here are different genomical expressions and how they interact. Okay, the different hypotheses, different model. If you ask somebody who's in more particles, he or she will tell you, okay, very important that you have particles in here and that they kind of interact. So it gets even another dimension to that. And then, of course, you can ask the physical oceanographer, oh, well, yeah, there's a boundary current, that gets unstable. And then you get signals propagating out. And yeah. And of course, then there are people that really are interested in commercial fish. So they want to know what these trophic levels, how they react in order to understand their fishing behavior. For example, bluefin tuna, this is oxygen in the Atlantic, and you can see these lines are bluefin tuna up and down dives, and you can see how they avoid the low oxygen environment here. So there is an interaction between them. So we, as a group, decided that this is way too complex, even if we would love to tackle that question. So we just concentrated on one kind of control surface, I would call it, which is the so-called oxycline. Oxycline is the region between very, very lot oxygen near the surface and then very low oxygen in the oxygen minimum zone. And the intensity of these oxycline is varying. And depending on this, this is now a time series from 50 years in the Atlantic, I think. And you can see that this region, the upper oxycline, is this white line here that increases, goes further up to the surface. This is now on 6 minutes. 6 minutes oxycline is here. And this is traced by acoustic measurements. This can be done because all the krill doesn't like to go into where no oxygen is. So the krill will always align with the oxycline, and therefore having this echogram tells you exactly over 6 minutes where the oxycline is changing. So there are changes on very long time scales, on very short time scales, and this is another just a feature where oxygen is very, very slow. So then we ended up in having some scientific objectives to be posed for the oxycline only. So we wanted to know what are the processes that create and maintain an oxycline. So we only now with this little surface. What drives spatial temporal variability of the oxycline? This is probably relatively, first of all, relatively closely related to that, which is primarily a physical problem, but it is also related to other points which come later, which I wasn't aware of, but biologists in the room said, yeah, but you have to think that this and that could also impact the oxycline. So what are actually the drivers in the vertical extent and the depth range? For example, do fish and so forth really affect the oxycline, or is it more the microbes that do it? Is the zooplankton vertical migration somehow being involved in creating and also kind of maintaining the oxycline? And what actually is the impact of oxycline variability on biomass abundance, community structure, and so forth, and fishing gear on the oxycline? So we have actually now to return back to this kind of graph and think about formulate hypotheses to all these little points here, and then bring them into one context. So what I wanted to show you with my presentation here is that, of course, we have multifaceted expectations of society and science on ocean information, and therefore we need a comprehensive, sustained ocean observing system in place. This is really very important, that we are not concentrating on one technology, but we need to have a multifaceted system of in situ and remotely sensing opportunities and observing systems. So there's a generic strategy on how to design actually the ocean observing, starting with a certain question, really specific question to answer, then identifying how we can find a scientific approach for that question, doing some mapping or whatever exercises in order to estimate the scales, and then evaluate the system and see if it's really fit for purpose, which means does it deliver against this question at the beginning. That includes other things like design, which is data availability, interoperability, mechanism to advance the system into the future, and also training and capacity. And with the last slides, I wanted to show you that there are many, many multidisciplinary problems out there that really covers in physics, biogeochemistry, biology. And we need new ideas actually in optimizing these kind of observing requests. Because that actually doesn't work any longer with a mapping. It doesn't even work with an OSSI, because as far as I see it, there's not really a model that can create a nature run, having all these different processes being working in parallel. That was it. Thank you.